This is video 3 for the waves unit. For this video, we're going to begin by talking about earthquakes, which are actually waves themselves. So when there's a fault in the earth, or when a fault in the earth suddenly releases energy, it creates a wave in the ground. So a fault line is usually where two tectonic plates meet, and they're kind of pushing against each other. So if one plate suddenly breaks free, it kind of gives releases a lot of energy. That energy then travels out as the wave, which we call an earthquake. The location where an earthquake starts is called the epicenter. So we can locate the epicenter of an earthquake by noting when the waves from that earthquake arrive at different locations. Just like the SOFR spheres were used to locate downed pilots in World War II. Moreover, the cause of the earthquakes is often deep underground, like 15 miles. So it can be kind of difficult to find the epicenter, but we can find it. Huge amounts of energy are released during an earthquake. Much greater than our largest nuclear weapons. So in 1935, Charles Richter found a way to estimate the energy from the shaking. His scale was originally called the magnitude local, and over time became known as the Richter Scale. So an earthquake with a magnitude of 6 is believed to release the energy about 1 million tons of TNT, so like a large nuclear bomb. Go up to a magnitude 7, and the earthquake releases about 10 to 30 times more energy. And that's because this Richter scale, it's not a linear scale. It's more exponential. So on this Richter scale, we can kind of see this overall trend. And on the y-axis, we kind of get an idea for like the energy released, whereas on the x-axis is what we call the magnitude. So for a magnitude 4 earthquake, it's a very minor event. Jump up to a 7, so an earthquake that has a scale of 7 is very strong. 8 to 9 is catastrophic, really bad. Now we can determine the speed of an earthquake wave. So first off, we understand that waves transport energy from one place to another. And the speed at which that this energy is transferred depends on many things, including the material, like the medium. Remember that the medium is the material through which the wave passes. Now, it is very dangerous when an earthquake moves from a high velocity material to a low velocity material. The reason for this is the same reason why tsunamis are dangerous. Tsunamis in open water where the water is very deep travel very quickly, but they have a very small amplitude. When the tsunami reaches the shoreline, where the water becomes shallower, the speed slows down and the water builds up and backs up on itself, and it causes the amplitude to increase. So the wave kind of gets taller in some ways. The same thing happens with the earthquakes. So when the earthquake wave slows down, its amplitude increases. And this is very bad for buildings. So the earthquake would do something like this, where we have very small amplitude to larger amplitude. So if we have a building sitting on this ground, imagine the low amplitude wave going underneath of it, just kind of rocks it back and forth, versus a high amplitude. It would topple the building much, much easier. Now, there are different types of earthquake waves. We got the primary wave, the secondary wave, and the long wave. So the P wave stands for primary. It's the first to arrive. This is a compression wave, or longitudinal wave, and it works just like sound does. The shaking is back and forth in the same direction as the wave propagation. So, for example, if you see a lamppost shaking in the east-west direction, that means you have a P wave. So, you're looking at this graphic here, we can see the wave motion is going back and forth. So this tree up here would shake horizontally back and forth. P waves travel at about 6,000 meters per second, which is a lot faster than sound. The S wave, or the secondary, is called a shear wave. And this is the wave that arrives second. This is a transverse wave, so its shaking is up and down. It's perpendicular to the wave's motion. So if the wave is traveling from the east, the shaking will be north and south, or up and down, sometimes an angle between. And we call this kind of shear wave. Shear waves can only travel through stiff materials, like rock. And this is how we know the core is a liquid. Shear waves do not travel through the Earth's core. So the S waves travel a little slower at around 3,500 meters per second. So again, here's our P wave shaking back and forth. So the S waves travel up and down. The S waves are more dangerous for buildings than the P waves. The last wave is the L wave, or the long or the last wave. These waves are waves that only travel on the surface of the Earth, sometimes known as Rayleigh Waves. They are a combination of the P and the S, and they're created near the epicenter when the P and S waves first reach the surface. They're called the long waves because they have the longest wavelength of the three types. They can usually cause the most damage because they typically have the greatest amplitude, and that's because they don't need to spread out as fast. So we see that the longitudinal waves travel the slowest at 3,100 meters per second. So again, here we got a graphic depicting the three types of waves. So we got the compression waves traveling back and forth. We've got the transverse waves, and then the longitudinal waves kind of rotate a little bit as they travel. Here's a time travel curve showing the three waves. So giving you an idea in time and minutes. So if we have the epicenter that is about 7,000 miles away or whatever, it takes about 15 seconds for the P wave to reach, and about 28 seconds for the S wave, and then about 56, about an hour for the L wave. So the S wave and the L wave are typically what we call the aftershocks from an earthquake. Waves themselves can cancel each other out or reinforce themselves. Now, we call this canceling or reinforcing superposition. Suppose that you are very unlucky and you're standing right in the middle of two earthquakes. One is coming at you from the north, while the second is coming at you from the south. And let's say that the one from the north is moving up, down, when it reaches you. However, the one from the south is moving down, up, down, up. What's kind of cool about this is that these two waves then will cancel each other out. The up from the first wave will overlap with the down from the second wave, and that'll cancel out. The down and the up will overlap, canceling out. And then the up and the down will overlap and cancel out. So while the wave from the north is moving up, the wave from the south is moving down. Now we call this destructive interference. So here's a graph of these two waves, and notice at all points these two waves cancel each other out. So I have wave plus wave equaling no wave. Now, if you can have destructive, you can also have constructive interference, which is double the trouble. So the two ups would overlap, making an even greater up. The two downs would overlap, making an even greater down. So those are destructive and constructive interference. This works for all waves. So sound is kind of cool using sound. You can have destructive interference with sound. So imagine this, sound plus sound equals silence. We can have this with light. Light plus light equals darkness. But we have to have very special conditions where the crest of one wave is overlapping with the trough of a second wave, or the compression from one wave is overlapping with the rarefaction of a second wave. So in this example, both waves have to have the same amplitude and frequency. If you have perfectly destructive interference, well, that's not always the case. Sometimes the two waves might have the same amplitude but different frequencies. So notice that's what I have right here. I have two waves that have the same amplitude. However, you'll notice that they're slightly out of sync. One has a different frequency than the other. Now, when that happens, occasionally they overlap and we have constructive interference. Other times, when they overlap, we get destructive interference, so like right here. This leads us to something called beats. You would hear a wah, 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 wah kind of sound. So what we get is we have this area of destructive interference where the waves cancel each other out, and this area of constructive interference where they reinforce each other, becoming even louder. And we would hear these beats every, you'd hear so many beats per second. So we basically have a frequency. So the frequency for the beats equals the frequency of the first wave minus the frequency of the second wave. So if I have two waves, one with a frequency of 500 hertz and a second one with a frequency of 495 hertz, we would hear a beat frequency of 5 hertz. So you would hear 5 wah 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 per second. Musicians then use this to determine if they're in tune. So when you're playing, two people are playing the same note, if you hear this wah 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 kind of sound, you're out of tune. And the process of tuning is trying to eliminate that. The next topic I want to discuss is the Doppler shift. So let's think that there's an object, or imagine an object emitting sound, like an ambulance or a police car. When the object approaches you, making it sound, you will hear a higher frequency than what the object is emitting. So the reason for that, this first dot right here represents something that's stationary. So it's a stationary source. The sound wave is spreading out evenly in all directions, as you might expect. However, if the object begins to move, it presses together the wave fronts in front of it. So the wavelength becomes shorter. Behind it, the wavelength gets longer. The speed of sound stays the same. So when we take a look at the speed equation, v equals lambda times f, if the wavelength gets smaller, the frequency must get higher. And if the frequency gets longer, the frequency must get down, must go lower. So what we see then is this rise in pitch. Now frequency gives us the pitch of a sound. So a higher frequency is a higher pitched sound. So think of a flute versus a tuba. Now this Doppler shift is seen in all waves, not just sound. The Doppler shift in light means that an object can be is either moving away from you. If an object's moving away from you, it's going to have a lower frequency shift, and if it's moving towards you, it's going to have a higher frequency shift. And this gives us red shift or blue shift in astronomy. The colors of light can be organized in Roy G. Biv, where as I get closer to violet, the frequency increases. As I get closer to red, the frequency decreases. So if I have a white star moving away from me, the light from it would, the frequency would dip, and it would give me like this reddish color. And if I have a white star approaching me, its light would kind of, the light from it would increase in frequency, and it would look a little more bluish. So this is how we can tell if stars are approaching or going away. Another thing is the fact that waves spread. We call this diffraction. So any wave, when it passes through an opening, will spread. So here we got some waves coming towards, imagine these like ocean waves coming towards like a break wall. If there's a hole in that wall, the waves go from like flat to circular. Also, this explains why waves can spread around a corner. Now, if it were not for the spreading, we usually would not hear people when they talk from like behind a corner, or if you're listening to someone speaking and you're standing outside of a door. Now, there is a simple formula that helps us calculate how much this spread happens. The spread equals the wavelength of the wave divided by the diameter of the opening times how far you are from the opening. So going back up here, the wavelength would be like the distance between the waves here. Diameter of the hole would be d. If I were to kind of measure this distance. This would be S, and this distance right here would be R. Let me get a better wavelength up here. And this model works for all waves, and it becomes very important for the design of telescopes and figuring out how far away something can be in order for you to see it with detail. So like spy satellites and things like that. All right, this concludes this unit.